Take a piece of ordinary ice. Hold it in your hand. It's cold, solid, familiar. Now try to set it on fire. It won't burn. Ice extinguishes flames. That feels like a fundamental law of nature. Except it isn't. Deep beneath the oceans, in darkness and crushing pressure, there's an ice that burns. Bring it to the surface, and it erupts into a bright yellow flame. Scientists call it methane hydrate, fire ice, and it may be the greatest untapped energy reserve on Earth, while also being the single largest climate time bomb humanity has ever faced. This is the story of a frozen paradox that defies intuition, challenges physics, and holds both our future energy supply and our greatest environmental threat inside the same crystalline cage. To understand how ice can burn, you have to enter the molecular architecture of this strange substance. Methane hydrate is what chemists call a clathrate, a cage. Picture a perfect geometric lattice made entirely of water molecules. But instead of being packed like normal ice, these molecules form hollow cages under extreme pressure. Inside each cage sits a single methane molecule, CH4, the primary component of natural gas. This structure only forms under a narrow set of conditions. Methane is naturally produced deep beneath the seafloor by methanogenic bacteria feeding on decaying organic matter. As the methane migrates upward through sediment, it encounters water near freezing temperatures and massive pressure. If the temperature is low enough and the pressure is high enough, conditions found hundreds of feet beneath the seabed or thousands of feet underwater, the water molecules lock themselves into cages, trapping methane inside. Nature turns gas into ice. And here's the astonishing part. 1 cubic foot of methane hydrate contains about 164 cubic feet of methane gas once it decomposes. Imagine a balloon the size of your living room being squeezed into a block of ice the size of a shoebox. That's the energy density we're dealing with. So where is all this fire ice hiding? The unsettling answer: almost everywhere beneath us. Methane hydrates accumulate in 2 major environments. The first is deep ocean sediments along continental margins, in regions called the gas hydrate stability zone. The second is in vast permafrost areas, Alaska, northern Canada, Siberia, where extreme cold replaces extreme pressure, keeping the hydrate stable just below the frozen ground. When scientists estimate how much carbon is locked inside these deposits, the numbers don't seem real. The total carbon stored in methane hydrates is roughly twice the amount found in all proven coal, oil, and conventional natural gas reserves combined. We are talking about trillions of tons of frozen fuel, enough to power human civilization for centuries. This is why countries like Japan, China, and the United States are engaged in a quiet technological race to unlock this resource. Methane hydrate could be a bridge fuel, a transitional energy source far cleaner than coal or oil. But harvesting it is incredibly difficult and dangerously unstable. Methane hydrate only remains solid under a tight combination of temperature and pressure. Bring it up toward the surface, reduce the pressure, or warm it even slightly, and it immediately breaks down into water and methane gas. Engineers currently test 3 main extraction methods: heating the sediment to melt the ice, depressurizing the formation to trigger decomposition, or injecting chemicals, like methanol, to destabilize the clathrate structure. But here's the problem. Methane hydrates are not just sitting there passively. They act as part of the scaffolding that stabilizes continental slopes. Disturb them too aggressively, and you risk triggering underwater landslides, massive ones, big enough to generate tsunamis. Even worse is what happens if methane begins escaping uncontrollably into the water column. Methane is a greenhouse gas with a global warming potential about 80 times stronger than CO2 over a 20-year period. If even a few percent of the methane stored in global hydrate deposits were released into the atmosphere, the resulting warming could be immediate, severe, and irreversible. This is where the terrifying concept known as the clathrate gun hypothesis enters the story. The idea is simple and frightening. If the oceans warm even slightly, or if Arctic permafrost continues to thaw, huge quantities of methane hydrate could cross their stability boundary. Once destabilized, they release methane gas. That methane accelerates global warming. The warming destabilizes more hydrates. More methane escapes. A runaway positive feedback loop. The gun fires, and the world enters a period of rapid, catastrophic climate change far beyond anything predicted by standard models. Geological history may already hold evidence of this gun firing. When scientists look back through deep time climate records, they find abrupt, violent warming spikes that cannot be explained by volcanic activity or changes in solar radiation alone. One of the strongest clues lies in the carbon isotopes trapped in ancient marine sediments. Normally, the ratio between carbon-13 and carbon-12 changes slowly. But at certain points in Earth's history, that ratio collapses almost instantly, indicating the sudden arrival of a massive pulse of light carbon. Carbon that matches the chemical signature of methane released from destabilized hydrates. These isotopic cliff drops appear globally and synchronously, which rules out local events. They point instead to a planet-wide trigger, a rapid release of methane from the seafloor or from thawing permafrost. Ocean cores extracted from the North Atlantic, the Southern Ocean, and the Arctic all show the same fingerprint, strong enough to overwhelm the entire global carbon cycle. Around 55 million years ago, the Paleocene-Eocene thermal maximum saw global temperatures spike dramatically over a geologically brief period. Carbon isotope records from marine sediments show signatures consistent with a massive, sudden release of methane, exactly what hydrate destabilization would produce. So the question now is unavoidable. Could it happen again? Scientists studying the East Siberian Arctic Shelf, one of the shallowest, largest hydrate reservoirs on the planet, have already documented methane bubbling through the water column as permafrost thaws. These are still localized seeps, not yet a runaway event, but they are warnings. They show the system is warming and loosening. This brings us to the deep paradox of fire ice. We're sitting on top of an energy source large enough to replace fossil fuels, provide geopolitical stability, and drive global power generation for generations. And at the same time, we are sitting on top of a geological weapon, one that, if destabilized, could push our planet into a new climatic state. Harnessing this resource requires an engineering precision humanity has never demonstrated at this scale. Ignoring it requires a level of climate stability the Earth no longer guarantees. We are caught between energy desperation and environmental danger, standing on top of a frozen reservoir we fear to touch, but cannot afford to lose control of. The ocean floor holds a secret that could save us, or destroy us. Fire ice is stable for now, but the climate is not, and the clock is ticking. If you were gripped by the scientific paradox of methane hydrate, hit the like button and subscribe. New videos every week uncover the hidden physics, geology, and mysteries shaping our world. Veil Origins. Impossible Truths.